Okay, welcome to the class. Today we're going to have a look at the third lesson in this chapter. We're going to have a look at the properties of light and then the interference of light waves. Young's double-slit experiment. Okay, so first let's have a look at properties of waves and light. The period from 1650 to about 1710 was significant in the development of theories of light. By the end of the 17th century, two opposing camps of physicists had emerged. One group followed the wave theory of light, and the other group followed the particles theory of light. The debate continued for over 300 years. In 1665, Francesco Grimaldi, who was the first scientist to use the term diffraction, suggests that observable diffraction took place when light passes through a narrow slit, creating rays of colored light, thus showing that light was wave-like in nature. Also in 1665, Robert Hooke developed his wave theory of light. Christian Huygens, in his treatise on light, further developed Hooke's theory that light behaved as a wave. Huygens formulated this wave principle called Huygens principle. Huygens principle states that all points on the wavefront can be thought of as new sources of spherical waves. Huygens also claimed that light required an invisible medium in which to travel, called the ether. Huygens' theory helped explain the concepts of reflection, refraction, and diffraction using wave concepts for light. However, a major objection to Huygens' ideas about light was that waves spread out in all directions. Isaac Newton, in contrast, thought of light as traveling in particles that he called corpuscles, or little particles. The particles travel in straight lines with maximum velocity and have kinetic energy. Newton's corpuscular or particle theory does not need a medium for light to travel in. This theory accounted for the rectilinear propagation of light, which means that light travels in a straight line. It also explained some other properties of light, such as reflection, and had some similarities with the much later theory of light. By 1700, Newton's theory still prevailed. It would be many years before direct experimental evidence countered Newton's views. In the early 19th century, Thomas Young seemed to disprove Newton's theory. First, he used a ripple tank to demonstrate the ideas of interference of water waves. Then he recreated Grimaldi's experiment, demonstrating the interference of light using a double-slit experiment. Young described how he placed a narrow card with a single slit in the beam of light and saw fringes of color in the shadow and to the size of the card. When he put another card before or after the narrow card to stop the beam of light from striking one of the edges of the card, the fringes disappeared. This result supported the theory that light is composed of waves, results that Newton's theory could not explain. So the question is that if light is a wave or a particle, in some instances, light behaves as a wave, such as during interference. Other times, light behaves as particle, such as light shining on metal. Okay, so first of all, let's have a look at Newton's particle theory of light. Newton's fascination with the ability of prisms to produce colors from white light led to his development of particle theory of light. He stated that light particles travel in straight lines, also known as rectilinear propagation, with a maximum velocity and therefore have kinetic energy. Newton's theory does not require a medium for the light to travel in. Furthermore, he was able to explain the properties of reflection and refraction using this theory. However, his explanation of diffraction showed the shortcomings of this theory. Okay, as you can see here in table 1, it summarizes Newton's explanation for these properties. Okay, first, a phenomenon called rectilinear propagation. This can be explained by Newton's theory. Newton argued that since light does not appear to curve but travels in a straight line, light must consist of particles with extremely high speeds. In addition, since he did not notice any pressure from light, the mass of the particles must be quite low. Next, the diffraction. Newton argued that light cannot travel around corners, as waves do. He argued that Grimaldi's observations were a result of collisions between light particles at the edges of the slit, rather than from light waves spreading out. Well, as to the phenomenon of reflection, Newton showed that if light particles undergo perfectly elastic collisions, the law of refraction follows from the laws of motion. Horizontal velocity does not change, but vertical velocity is reversed, causing the particles to bounce. The magnitude of the velocity does not change. Okay, last, refraction. Newton claimed that particles will bend towards the normal if their speed increases. Particles accelerate at the boundaries as they pass from one medium to another, and the speed in the medium is greater than in the air. This is the opposite of what actually happens. Okay, next, let's have a look at Huygens' principle and the wave theory of light. Huygens' principle leads to a geometric construction that determines the position of a new wavefront based on knowledge of the previous wavefront. So here, as we can see in figure 1a, the straight wavefront AB is moving towards the light. The straight wavefront AB in figure 1a corresponds to a circular wave from a wavefront AB in figure 1b. Huygens' viewpoint is that all the dots on the straight wavefront can be considered as new sources of spherical waves. The small arcs of circles shown in figure 1b. The wavefront A prime B prime is the new position of the wavefront a short time later. Also notice how A prime B prime is a tangent common to all the wavelets. Okay, so as we can see here in figure 1a, in Huygens' construction of a straight wavefront, the wavefront is just a straight line, even though it is defined by circular waves. And in figure 1b, in Huygens' construction of a spherical wave, the new wavefront is drawn tangent to the circular wavelets, radiating from the point sources on the original wavefront. Okay, next, let's have a look at how Huygens principle can be used to explain reflection. Huygens principle shows a deviation of the laws of reflection and refraction. Figure 2 here shows simplified wavefronts striking a surface. At the point where each wavefront contacts the reflecting surface, a wave reflects. Figure 3 here simplifies reflection even further by showing one incident ray and one reflected ray, obeying the law of reflection. Okay, next, Huygens principle can also be used to derive Snell's law of refraction, as illustrated in figure 4 here. Remember that in time delta t, the portion of a wavefront moving in the first medium covers the distance v1 delta t, right? The portion moving in the second medium covers a distance v2 delta t. If the second medium is a slower medium, the portion of the wavefront in the second medium moves a shorter distance. As a result, the wavefront and the ray deviate from the original path in medium 1. Since the waves in medium 2 do not travel as quickly, it will take longer to move away from the normal line, right? As a result, the refracted light ray is closer to the normal. We have already known this in previous chapters. This difference in path length results in the law of refraction. Applying trigonometric relations to figure 4 to take account of the differences in path length results in a deviation of the law of refraction. So in Huygens' explanation of the law of refraction, the wavefronts bend due to differences in the speed of light in two media. In this figure here, the wavefront is traveling faster in medium 1 than in medium 2. Okay, so now let's make a summary. So this table shows or summarizes the application of Huygens' principle to the properties of light. Also, we'll talk about the four phenomena separately. First, the rectilinear propagation. Each point on the wavefront acts as a point source for a new spherical wavelight, and the wave propagates away from the source. So that's the explanation by Huygens' principle applied to the phenomenon of rectangular propagation. Okay, next, diffraction. This can be explained by that each point passing through an opening acts as a point source for new spherical wavelets. Huygens' principle is consistent with large slit widths, edges of opticals, and slits of the same magnitude as the wavelengths. Okay, third, reflection. This can be explained in that the incident ray hits points on the reflecting surfaces, which then acts as point sources for spherical wavelets. Last, refraction. The difference in the speed of wavefronts traveling in the two media causes a wave to bend towards or away from the normal, which is shown here in bottom left. When the speed of wavefront decreases, the wave refract towards the normal. So Huygens' wave theory explained many of the properties of the light, including reflection, refraction, partial reflection, partial refraction, diffraction, dispersion, and rectilinear propagation. Although the wave theory made a strong case, Newton's principal theory dominated for much of the following century. This dominance was due largely to Newton's undoubtedly success in other scientific areas, including studies of gravity, which gave him immense prestige within the scientific community. Then, Newton's theory went into decline after Young's double-slit experiment demonstrated interference of light waves, which we'll read about in the second half of this lesson. Okay, so before we move into the second part of this lesson, interference of light waves, you can now take a 10 minutes break. Okay, you can have a look at the Newton's particle theory of light and Huygens wave theory of light, and compare these two series by yourself. Okay, I'll give you some time to do this. Okay, next let's have a look at Young's double-slit experiment. So at the end of the 1600s and into the 1700s, the debate over the nature of light was in full swing. Newton's theory of light particles faced challenges from leading scientists such as Christian Huygens. Huygens' writings on the wave theory of light described what we now call Huygens' principle and proposed that light traveled in waves through an omnipresent ether, like sound traveling through air. Mathematician and scientist Leonard Euler developed his own wave theory of light and used the particle theory's poor description of diffraction as a key point in an argument against Newton's theory. During this time, many researchers focused on the question of interference. If light travels as a wave, then it should interfere like a wave. Experiments looking for interference, however, could not detect it. We now know that the experiments failed because of the extremely small wavelengths of light. Interference patterns in water waves in ripple tanks are easy to observe because the wavelengths are large and the frequencies of the sources are relatively small. These properties make the distance between the adjacent nodal lines visible to the eye. Most experiments with light before the 19th century involved the placement of two sources of light close to each other, with screens positioned near the sources. Scientists closely observed the screens to try to observe interference patterns. They never succeeded using this method, partly because the separation between the nodal lines was too small to be observable. However, these issues did not account for all of the problems in attempting to repeat the ripple tank experiment with light waves. Atoms, including those in the sun and in light bulbs, emit most visible light. We might expect the light waves emitted by two atoms in the same source to be identical and have the same frequency so that they could exhibit interference. However, collisions among atoms can reset phase of the immediate light waves. Experiments show that these phase jumps in typical light waves occur about every 10 to the power of -8 seconds. This means the light from different atoms of a given source is incoherent because the waves have no fixed phase relationship to each other. Well, if we direct light from a monochromatic, a single wavelength source through a narrow slit. However, the slit acts as a single point source, and the light travels from it as a coherent wave according to Huygens' principle. If we then direct the light from the single slit to a double slit, or a closely spaced pair of slits, the double slit acts as a pair of sources of coherent monochromatic light, which is shown here in figure 1. Any change that occurs in the original source will occur in the two beams at the same time, which allows us to observe interference effects. Okay, so next let's have a look at the Young's double-slit experiment in detail. At the very end of the 18th century, Thomas Young performed a series of experiments to determine what happens when light passes through two closely spaced slits. We now refer to his basic setup as Young's double-slit experiment, and it demonstrated conclusively that light behaves as a wave. The experiment also provided a method to measure wavelengths. So here, figure 3a shows the experimental setup, and figure 3b on the right side shows an image produced with such a setup using white light. When monochromatic light, such as laser light, passes through the slits of an experimental setup, similar to the one in figure 3a, the laser light hits the green on the right and produces an interference pattern. This arrangement satisfies the general conditions required to create wave interference. These conditions are: first, the interfering waves travel through different regions of space. In this case, they travel through two different slits. Second, the waves come together at a common point where they interfere. In this case, the screen. Third, the waves are coherent. In this case, they come from the same monochromatic source. So when the two slits in the double slit setup are both very narrow, each slit acts as a simple point source of new light waves, and outgoing waves from each slit are like the sample spherical waves in figure 4. Well, in this figure, we can see the diffraction effects of light passing through two narrow slits by considering just one of the narrow slits. The same thing happens in the second narrow slit. So interference will determine the intensity of light at any point on the screen. If one of the slits is covered, the screen shows a bright white center line with closely spaced, dim, alternating dark and light bands, or interference fringes on either side. We can read more about the single slit pattern in next chapter. We'll talk about this later. However, if both slits are open, then the screen shows a pattern of nearly uniform bright and dark fringes, which is shown here on the right in figure 5. The ideal double slit pattern would show no dimming, but the real-world pattern does appear dimmer as we move away from the center. This dimming occurs because the width of the slits causes each to act like a single slit, and the non-uniform single slit pattern combines with the ideal double slit pattern. All right, so the bright and dark fringes are alternate regions of constructive and destructive interference, respectively. To analyze the interference, we need to determine the path length difference between each slit and the screen. So here, figure 6 illustrates the double slit interference conditions. Okay, so let's have a look at the mathematical principles in the double slit experiment. Okay, so in figure 6a, values of theta gives the location of the bright fringes on the screen. And as shown in figure B, when the point P is very far away compared to the separation of the two sources, the line L1 and line L2 are considered nearly parallel, okay? So to simplify the analysis in figure 6, we assume that the screen is a long way from the slits. In that case, L is very large compared to D. The path lengths for waves from each of the slits to the point P on the screen are L1 and L2 in figure 6. Then the distance L2 is greater than the distance L1. And since L is large, the angles that specify the directions from the slits to point P are approximately equal. So here, we can consider theta prime here is approximately equal theta because the screen is very far away from the two slits. Okay, so L1 is approximately parallel to L2. So both are shown as theta here in figure 6. Finally, we assume that the wavelength lambda is much smaller than D, the spacing between the slits. Okay, since the slits are separated by distance D, the path length difference between L2 and L1 is here. You can observe this in this diagram. In this diagram, we have, this is path difference, right? Here. This is the path difference between L2 and L1. And in this right triangle, we know that delta L, this is delta L. This is our delta L. Delta L equals D times sine theta, according to the definition of sine in right triangle. For the two waves to be in phase when they reach the screen, and thus for constructive interference to occur, we know that this path length difference needs to be a whole number of wavelengths, right? Okay, listen again. For the two waves to be in phase when they reach the screen, and thus for constructive interference, this path difference, or delta L, needs to be a whole number of wavelengths, okay? The condition for constructive interference and a bright interference fringe is therefore given by this relationship here. Delta L is D sine theta, right? D sine theta needs to be a whole number times wavelength lambda, where m equals 0, 1, 2, 3, and so on. In this case, we'll have constructive interference and thus a bright fringe. The light fringes or maxima are called zero order maximum, first order maximum, and so forth. For m equals 0, 1, 2, 3, and so on. Okay. In this notation, m equals 0 denotes the maximum in the center of the screen. Successive values of m corresponds to successive maxima moving away in either direction from the center of the screen. For the two waves to be out of phase when they reach the screen, and thus for destructive interference to occur, the path length, delta L, needs to be n minus 1/2 times the wavelength lambda, right? Which is shown here in this relationship. Thus, the condition for destructive interference and the dark fringe in the interference pattern is given by d sine theta equals n minus 1/2 times lambda. Understand? Where n equals 1, 2, 3. These are the conditions for destructive interference and then dark fringe. These dark lines or minima are called first order minimum, second order minimum, and so forth, for n equals 1, 2, 3. Okay, so here, figure 7 shows a much enlarged intensity pattern from a double slit experiment. Notice here that as the value of m changes, the angle theta also changes. At certain values of theta, the conditions for constructive interference are satisfied, and a maximum in the intensity is produced, corresponding to a bright fringe. The fringe at the center of the screen is called zero order maximum and has a value 0 for m in the equation for constructive interference. The next bright fringe moving towards the top of the screen has the value m equals 1, and so on, which is shown here in figure 7. Okay? So this is where m equals 0. You get bright fringes. You get bright fringe. Here m equals 1. Here m equals 1, and here m equals 2. At these locations, these are the maximums. And these locations will get bright fringes. And using this relationship, d sine theta equals m times sigma. This really connects the 4 variables, okay? We can measure d. Also, we can measure sine theta. Then we know the order number m. Then actually from this experiment, we can get the wavelengths of this monochromatic light. We'll talk about this later, okay? Okay, so how does the interference pattern change when the distance between the slits changes, or when the distance to the screen changes? Let's have a look at this. First, calculate the separation between the central bright fringe, where m equals 0, and the next bright fringe, where m equals 1. The equation for constructive interference tells us that sine theta equals lambda over d, right? To determine the separation between the bright fringes on the screen, we can use the right-angled triangle outlined in red here in figure 7. It has size of length L and X. Sorry, X1. Where X1 is distance between the two fringes corresponding to m equals 0, which is here, and m equals 1 here. These lengths are related by a trigonometric relationship. X1 equals L tangent theta, right? Then the wavelength is the wavelength is much smaller than the spacing between the slits. So so lambda over d is very small. Therefore, theta is also very small. And approximation sine theta equals tangent theta can hold. Therefore, we have this approximate relationship. Okay, when theta is small, tangent theta equals sine theta. Right? So x1 equals L sine theta. That means x1 equals L lambda over d. You see that? Because sine theta is lambda over d. So if you substitute sine theta with lambda over d, then x1 equals L lambda over d. Then for the mth order right fringe, this relationship becomes here. Okay, xm equals m L lambda over d. This is for the mth order right fringe. And the separation between any two adjacent fringes is given by this relationship. Delta x equals lambda L over d. Okay, this is the separation between any two adjacent fringes. Okay, so let's use this formulas to have a look at example here. Suppose the slit separation is 0.1 millimeters. The wavelength of light from a right laser is 630 nanometers. And the screen is 0.5 meter from the slit. Then using this formulas, we can substitute the corresponding values into this equation to determine the separation of fringes for the red laser light. Well, delta x, you can see here, delta x equals L lambda over d. Put all the values in, delta x is 3.2 millimeters. So the separation is large enough to be seen by the unaided eye. So this analysis shows that provided the slits are close enough together, the bright and dark fringes in the interference pattern are observable. A slit separation of 0.1 millimeter or smaller works well. Experiments have shown that when the spacing is larger than a few millimeters, the fringes are close together and difficult to see. All right, using the equations for destructive interference, we can calculate the distance of each dark fringe from the center of the screen. So the idea is similar, right? First of all, we know xn equals n minus 1/2 times L lambda over d for n equals 1, 2, 3, and so forth. For example, the distance for the first, second, and third minima from the center of the screen can be calculated as follows. First, second, third. For example, the distance of the first minimum from the center of the screen is x1 equals 1 minus 1/2 times L lambda over d, which gives us L lambda over 2d, where x2 equals 3 lambda L over 2d, and x3 is 5 L lambda over 2d. Although L actually has different values for each nodal line, In this case, L is so large compared to D, and the values of L for the various nodal lines are so similar that we can treat L as a constant, being essentially equal to the perpendicular distance from the slits to the screen. Okay, modern interference experiments often inject a cloud of smoke between the slits and the viewing screen. Some of the light reflects off the particles in the cloud, so the viewer can easily see the path of the light. Will interference patterns appear in the cloudy region between the slit and the screen? The equation for constructive and destructive interference depend on the distance L from the slits, which can be any value considerably greater than D. The interference patterns will still occur in both places. In the cloud region, you will see bright lines directed towards the bright areas of the screen, and dark lines directed towards the dark areas of the screen. Okay, so use what we have learned so far. Let's consider a problem here. Okay, so we have a double slit experiment. It was carried out with slit spacing D equals 0.41 millimeters. The screen is at a distance of 1.5 meters. The bright fringes at the center of the screen are separated by a distance delta x equals 1.5 millimeters. Can you calculate the wavelength of the light? Well, as I just said, you can use the formulas we have learned here to calculate the wavelength of the light, right? Here. Or here. You can use these formulas to help you to calculate wavelengths. Okay, so have a look at this question here. I'll give you 2 minutes. You should be able to quickly get the answer, okay? Okay, have you finished? Okay, let's have a look at the result. Okay, so in a double slit experiment, the bright fringes occur when light waves from the two slits interfere constructively, right? Oh, this happens when the path difference, delta L, is equal to a whole number of wavelengths. So we have the following relationship. Delta X equals L lambda over D. Therefore, lambda equals delta X times D over L. We know delta X, we know D and L. So put all the values in, we have the wavelength lambda equals 4.1 times 10 to the power of -7 meters. Any questions? No? Okay, so this is a important relationship you should understand, okay? All right, then let's consider another problem. Okay, suppose the third order dark fringe of 660 nanometers light is observed at an angle of 20 degrees, 20.0 degrees, when the light falls on two narrow slits. Can you determine the slit distance? Let's have a look at the solution here. Well, for dark fringes, we have following relationship, right? D sine theta n should equal n minus 1/2 times lambda. Therefore, we know the separation of the two slits D should equal n minus 1/2 times lambda over sine theta n. So in this case, we know that's the third order dark fringe. So n equals 3. Lambda equals 660 nanometers, and theta equals 20 degrees. So use a calculator, you can find separation between the two narrow slits. D equals 4.8 times 10 to the power of -6 meters. Okay, so next let's have a look at some more developments in the theory of light. Young's evidence for the wave nature of light was not accepted by the scientific community until 1818, when Augustine Fresnel proposed his own wave theory, complete with mathematics. A mathematician named Simon Huygens showed how Fresnel's equations predicted a unique diffraction pattern when light is projected past a small solid object, as shown here in figure 8. So here in figure 8a, that shows a prediction of Fresnel and Poisson, confirmed by Argo says that the diffraction will cause a small bright spot to appear at the center of the shadow of a small solid object. And here, figure 8b shows a small disk refracts light and shows Poisson's bright spot. So Poisson's argument was that if light behaved as a wave, then the light diffracting around the edges of the disk should interfere constructively to produce a bright spot at the center of the diffraction pattern. This was impossible according to the particle theory of light. In 1818, Poisson's prediction was tested experimentally by Dominique Argo. And to many people's surprise, he successfully observed the bright spot. Argo's experiment demonstrated what is now called Poisson's bright spot. The wave theory had been generally accepted by 1850, although it could not explain the movement of light through a vacuum, such as space. Therefore, as mentioned in previous section, scientists develop a theory that a fluid called ether filled all regions of space. Despite many experiments devised to try to detect this ether, it was never found. Okay, so that concludes our lesson for today. I'll see you next time.